today what we will do is the analysis of the structural modeling. Essentially, we will do the deformation of structures and influence coefficients. Okay. Because we have said that aeroelastic problem consists of structural modeling, aerodynamic modeling, inertia modeling. So the first thing is we will start with the structural modeling. And just for the sake of understanding, you say a cantilever beam, okay, and this is a highly approximate idealization of a wing, you can take it. If you put a load somewhere, that's going to deflect. Now assuming linearity, you will say load versus deflection. Q is the load and you say this is the lowercase q is the deflection at the point of application of the load. The load can be a force, it can be a moment. If you write linear relation, you will have deflection is some constant times q load. You call this as the influence coefficient. Okay. Because this is sometimes also referred as flexibility influence coefficient. Okay. Because everything is within the elastic limit. I apply the load, it deforms, I remove the load, it goes back to the original state. Okay. And now if you want to know what is the work done, the work done by the load essentially goes and stays as the energy stored in the structure. So that you will write it as, because you are writing this like this, so you will have deformation versus q, it will be like a straight line. Okay. Now the energy, which you call it energy stored in the structure, you will write it as half q, that's all, any q. Okay. This is the strain energy, you call it. You can substitute for this and you will write it as half C q square. This is one way of writing the whole thing. Now this is for simple single load, very basic thing. Now if you have more number of loads, it's not just only one, you may put qi, you may have another one like qj, like that. You have several loads. You assume, because it is the very first thing is you assume it is a linear problem. Linearity is assumed. Okay. The loading is within the elastic limit, therefore, and it is a linear restraint type of load deflection curve. Then you can directly go ahead and write principle of superposition is applicable. So you say linearity means I apply principle of superposition. Okay, is applicable. Then you can write your deflection in a summation form. Qi is the deflection at point I due to Qj, j running from 1 to, you may have n loads. Now I also runs from 1 to n locations. Okay, that means Cij now becomes, you call it influence coefficient matrix, because this is like deformation at I due to a unit load at j. Okay, unit load, and you are just summing it up. Now this you can put it in matrix form, which will come as Q is C. Okay. Similarly, you can write the load in terms of deflection. Like spring, you write it F is equal to Kx, where K is the stiffness. Please understand, here C is flexibility, where you write F equals Kx, K is stiffness. Now you can also write using the stiffness type of thing, load is given in terms of okay, this is stiffness influence coefficient matrix, or you can leave it as it is. Okay, this is flexibility influence coefficient. Okay. Now what is the relation between this? You can substitute this Q here, then you will get K C Q. That means this must be identity. So stiffness matrix is inverse of flexibility influence coefficient, either or this is inverse of this. Now apart from this, this is written in matrix form. The influence coefficient matrix has another important property, which is it is symmetric. Okay. Now the symmetry has to be proved. First we will do in this matrix notation, later we will take a continuous loading. Okay. How do you get the symmetry? Because this is an important property of the influence coefficient matrix. This is based on, this is the reciprocal theorem, they call it Maxwell and Betti, okay, reciprocal theorem. Okay. It all goes down to the strain energy the energy stored in the structure during the deformation. It's like this. Suppose we have taken this case, we applied two loads. We applied actually two loads, right? One here, another one here. This we call it J. Okay. Now, which sequence they are applied? Whether you apply this first and then this, or you apply this first and then this. Now, in terms of final deformation of the structure, you say it is independent of the sequence of loading. Okay. And that means the energy stored in the structure because of the application of this load, it really doesn't matter which one is applied first, which one is applied later. Okay, because this is linearity is again is very, very important. Okay. So we will just prove that because that is a very important thing. Suppose you take a structure, okay, and fix it here, have some fixity here also, and there are some notations which we will use it, because this we say delta I, okay, and this is alpha I. Delta I is, this is the location I. Delta I is the linear deflection. This is angular deflection at the point I. At that location, you can take it, because the point doesn't have a rotation. You can always say that zone. Now you can take another, which is J. Here this is delta J and this is alpha J. 2 points. Because we are taking both translation as well as rotation in that, because the structure can deform. You can also have a rotational deformation, angular deformation. Okay, that's why it's taken generally. Now if I have a load Fi applied, I am only assuming that two loads are applied. I can apply 4. And at location J, I am putting a Mj, a moment. So this is the force, this is the moment Mj. Now using this, let us try to find out what is the strain energy of the structure due to this loading. If you say the strain energy U, we first start with, okay, sequence is I first apply Fi and then Mj. That means first Fi, then Mj. Okay. Now you need to write the strain energy. What is that? First, when I apply Fi, it is going to have some deflection. That deflection at point of application, because you don't, other points also will deflect, but you have to look at what is the deformation at the point where the load is applied. So you will write half Fi deflection due to the load Fi. So I am going to use that influence coefficient form Cii delta delta. Please note that this is a notation. This is point of deformation, point or point at which you are measuring the deformation, you can call it, and this is point where load is applied. Okay. Now this is type of deformation. Okay, and this is type of load. Okay. So you see, I am using actually two subscript, two superscript to indicate. One is where is the location my load is applied and what type of load is applied, whether it is a force or a moment. Then similarly, the point where I am measuring the deformation, whether it is a translational or rotational deformation. So one is the point of load, another one is point at which you measure the deformation. Okay. Now I have to add the other. This is first the energy due to only applying load Fi. Okay. Because this is nothing but the Q at that point, the deflection at that point. Now I said first Fi I applied, so this is the strain energy it stores. Then I am applying Mj. That means I have to add the energy due to the load Mj. Now this load Fi is fixed load, okay, and that will move through some distance, right? What is that? That will be Fi into, you will have C I delta J alpha Mj. Okay, because Mj is the moment which I am applying here. Because of this moment, what is the deflection here? Okay, so that is why J is the location my load is applied, and what type of load? It is a moment. That is why alpha, rotational load. Where is the deformation? At location I. What type? It is a translational or linear deformation. Okay, and the load is F into distance. That is the energy work done by this load. Now work done by the load Mj you will write. That will be half Mj C J J alpha alpha Mj. Okay, is it clear? So that is why the notation is very, very important. Where you measure the deformation, where the load is applied, and what type of deformation, what type of load. Okay. Now if you change the sequence means I am applying Mj first and then Fi. I will have U is half Mj C J J alpha alpha Mj. Okay. Moment, angular rotation. This is the first one. Next I am applying the load Fi. That means this moment which is already applied here, it will rotate through some other angle. So that means I will have Mj, I'll put C J alpha and I delta Fi. Okay. This is the rotation at point J due to a load at Fi plus half Fi, then you will have C I delta I delta. Okay. Now you say that it is independent of the sequence of loading. Once you specify, you will find that you have to equate both of them, both these expressions. When you equate, you find that MJFY, MJFY. Here Ci delta J alpha, here it is Cj alpha I delta. And if the strain energy of the structure is independent of the sequence of loading, that means that must be same, equal. So you will have Ci J delta alpha is equal to C J alpha I delta. This is the. Now we can write a very general expression, which I will write it. You can write the strain energy also in a different form. So I will erase this. So put it in a. Suppose this is delta I alpha I, delta J alpha J. You can fill up the full 4 by 4 matrix. Okay, that will be Cii delta delta, Cii delta alpha, Cij delta delta, Cij delta alpha. This is multiplied by Fi Mi Fj Mj. So I will fill the whole thing. You will have Ci alpha I delta, I alpha alpha, Ij alpha delta, Cij alpha alpha. Cji delta delta, Ji delta alpha, Cj j delta delta, Cj j delta alpha, and then Cji alpha delta, Ji alpha alpha, Cj j alpha delta, and Cj j alpha alpha. Okay, this is the complete for the two loads. Please understand, this is how it will look like. Now, if you have more number of loads, the size of the matrix is going to become bigger and bigger. Now later, if you have distributed loading, we are going to put everything instead of matrix notation, we will put it in the integral form. Okay. Now we can write the strain energy, this part, also in a different form using this. Okay. Now for the same case, what will, I think I will erase this part because this is maybe I will erase this part. Okay. Now using this, if you have only these two loads, your delta I is Cii delta delta Fi plus Ci sorry Cij delta alpha m j, because this is the total deflection at point I due to both the loads. Because here you have Fi mj, these two are 0, so you have I delta, that's all this term. Now similarly you can have alpha j, that is the total rotational deformation at point j due to both the loads. You will have C j I alpha delta Fi plus C j j alpha alpha m j. Okay. Now what you do is, this expression you split it into two parts. You write it as half. So maybe I will put it. You can write this particular expression. Write half Fi Cij delta alpha mj. So I can write it as Cij delta alpha mj. This is the first. Another half, I am writing it as half. Again you can write it Fi, but I will change it to, because you know that this is same as this. Okay. So I can put half of it. That means C j alpha I delta mj, but I remove this, I will put it like this. Okay. Now what I do is I take this term, add it to this part, I take this term, add it to this part. Then my expression will be U equals half Fi. This term will remain as it is, Cii delta delta Fi plus I will have Cij delta alpha mj plus half, I am taking this term mj Cj alpha alpha mj plus I am writing this term, because this is mj, I am taking it out. So C j alpha I delta. So C j alpha I delta F I. Okay. Now you see this term is nothing but delta I, and this is nothing but alpha j. Okay. So you write your, this is half Fi delta I plus half mj alpha j. Okay. Now you see, in that form of expression, it is the load and the total deflection at that point of application of the load and half. So you can write your very general energy expression as, maybe I will erase all this part, it is all gone now, it is not necessary. U is half summation Qi, that's all. Okay. Now if there are n loads, not 2 loads, n loads, you will simply put I running from 1 to n. Okay. You can replace, but you know that how you have represented the Qi. Qi you have represented as summation Cij Qj. This is j running from 1 to n, right? I can go back and substitute here and write my strain energy expression. Okay. I can write my strain energy expression as U half summation I running from 1 to n, summation j running from 1 to n. I will just put this Qi Cij Qj. Okay. Right. And this itself can be written in matrix form as half Q C Q, or you can say Q transpose CQ. Okay. And you can put it in stiffness form also, either way. So this is the energy expression. If you want to write it in stiffness expression, this will be what? Q is Kij Qj. So again you will be able to write it as half Q transpose, okay, K Q. This is the stiffness form. This is in flexibility form. This is how you define the strain energy in the structure, and the important property is it is symmetric. Okay. I think see, we have till now considered only discrete loads. Suppose you take a continuous load. That means the loading is not specific, because this is a matrix form we got. Let us take, for example, same. The wing is represented as a cantilever beam. This is acted on by a aerodynamic load or external load, I will put it. This is acting. This is the external load. This is distributed. Okay. All right. And this is going to deform. This will have some a deformation. Now for this we need to get, because this is what our realistic case is. You have a distributed load, you want to know how the wing deforms under the action of a distributed load. Whether it is a bending or a tension. Here we take a bending thing. And let us define the axis system. First let us say this is, I think I use the symbol Y, okay. And I also use another notation which I call it eta, and this is d eta, okay. And the external load I am going to call it as z y, because this is the function of y, okay. Now the load that acts at this location is essentially Z eta d eta over a small elemental length. The load acting is this. Now the deflection at any other point due to only this load is, you will write is that d, I am taking deformation, this is w, which is a function of y. Okay, w is a function of y, that is a bending deformation. Now this is an elemental load, this is an elemental load. I will have dw, which is a function of y, is y is the running variable, please understand, whereas this eta is a fixed at this point. Now you know that the loading is z eta d eta, there must be some influence function. That influence function we will write it as c y comma eta. Okay. That means this factor c y eta represents at deformation at y due to a unit load at okay. Now if you want total deflection, what you have to do is you have to integrate. So total deflection means deflection due to all the loads. Now that integration is over d eta. So here that will become, so now you can write it as w at any y will be integral 0 to L. L is the length of the, if you say this is the total length is L, okay, this will be c y comma eta z eta d eta. Okay. Now this is called again flexibility influence function. Okay. Actually, if you really see, this is easy to make a measurement in experiment, because what you do is you put unit loads at several locations, simply go and measure the deflection at every point. Okay. On the other hand, the modified form is stiffness influence function. That's difficult to formulate because it is not easy, because stiffness influence you will be writing it in this fashion. Actually what you want deflection, that is force at any point in terms of deflection at all the points. That means you will be writing some, okay, k, this will be w eta, okay. This is difficult to, this is the stiffness influence function. Okay. This is difficult to get. Okay, discrete system it is easy, but experimental measurement always you will find this flexibility influence coefficient is easy. You can go take a wing, put it on a test rig, put suitable boundary condition, and then apply the load, and then keep making measurements at every point. You can form the matrix because you have to make a grid, and then you can get this. Then you can have interpolation. Now you see, this is how the structural deformation is measured. Suppose if you know the pressure on the aerofoil at various points, because this is what either CFD calculation or any of the calculation. You know the pressure into some area, that is the load. Find out the deflection, you know what is the total deflection on the entire wing. But now the question is, how do you get this? Okay. We have given everything in terms of just mathematical form. Now you need to know, how do I get this? Sometimes this is also called influence function. I read people use sometimes green function, but we will use it as a flexibility influence function. Okay, influence coefficient function. If you want to put coefficient also, okay, that's fine. This is where the structural analysis comes. How do I get this function for a given structure? Okay, this is what you have learned in structures 1 course. If it is a beam under bending, or a plate model, or beam under torsion, Saint-Venant torsion, all those theories are applied here to get that flexibility influence function. So what we will do is we will take the same problem, and please note, this is symmetric. Symmetric in the sense C y eta is equal to C eta y. So in a functional form also this is symmetric. So C y eta is equal to C eta. Okay. This is symmetric function. Symmetric means you change the position of this, change the, wherever y is there you put eta, wherever eta is there you put y, the function remains the same. Okay. Now we will take a same example of the beam problem, and we will try to what is the C y eta, and then write this general expression. Okay. Now let us take the same problem. First, we need to, our idea is to evaluate this. This is the same cantilever. Let us assume a unit load is applied at location eta, and you want to find out the deformation this is C y comma eta. Okay, and this is y. Okay. Now for this case, we assume that Euler-Bernoulli beam theory. Now you see what Euler-Bernoulli beam theory we use it. You all know what is that Euler-Bernoulli beam theory is. It's a simple theory. Plane section remains plane and perpendicular to the reference line before and after deformation, because there is no shear deformation on the beam. Okay. Now, what is the bending moment at various locations? The bending moment M at any y. Please note that my load is at a fixed location eta. Bending moment at any location y, that depends on, I'll put, if you want more specifically, m eta. Eta is the load application point, y is the location where you are getting the bending moment. This will be eta minus y when y is okay, and this bending moment is 0 for y greater than, actually y equal to eta, it's exactly 0. Okay, that means you have split the whole beam into two parts. One part you have a bending moment which is eta minus y. That means when y is in this zone and y beyond this point. Okay. Now you solve the equation of just bending deformation. You know the bending moment, and Euler-Bernoulli beam theory says that bending moment is equal to what? EI. This is the load. This is EI d square over d y square w at y. Right? This is the standard second derivative of the deformation. Now what is wy? Because we know that wy, no other load is there except only one load. So dw is w itself. That is nothing but cy eta only. Okay. So this becomes essentially EI d square by d y square c of y comma eta. Okay. So this is my equation. You have to solve. You know the moment is given here. Substitute the moment here, solve for cy eta, but in two parts of the beam. Okay. So with the boundary condition, that is the key. Now let us take the first case. The first case is EI d square c dy square equals eta minus y for y less than or equal to eta. So we solve this part. Now you can get EI dc equals eta y minus y square over 2 plus some constant a1. I am integrating. Now you know that boundary condition, when y is 0, load is applied at eta, unit load. When y is 0, the slope of the beam, because it is a cantilever beam, this is where your assumption now starts coming. What is my boundary condition? Boundary condition, I say w at 0 is 0, dw by dy at 0 is 0. Okay, dw by dy becomes basically because w is c, so the prime. Therefore, you will have the boundary condition dc 0 comma eta over dy. This is 0. Now when I substitute y0, I will get this condition leads to a1 equals 0. Okay. Then what I do? I do one more integration. When I do one more integration, I will have ei c y comma eta equals, now I am integrating this. This will be eta y square over 2 minus y cube over 6 plus another constant I will put a2. Again a2, I know that deflection at the root is 0. So I will have c at 0 comma eta, this is 0. So this gives me a2 is 0. Okay. All right. Now you have got the function c y eta in the zone y is less than eta. Okay. So we will write it maybe, okay. I write here possibly, yeah. So I will put it here c y comma eta equals eta y square over 2 minus y cube over 6 1 over ei. This is for y. Okay. All right. Now let us go and do the other part where the second half where y is greater than eta. The bending moment is 0. Okay. So I will have now what? I will have a constant. Okay. This I call it as a3. Now what is the value of a3? You have to determine from the earlier case at y equals eta, what is the value? Okay. That is, if you write that, maybe I should write it here. Where do I write? Maybe I will write here. That's the best. Because we got, what is that? C prime y comma eta. This was actually 1 over ei eta y minus y square over 2, and when y equals eta, this will become c prime y comma, sorry, c prime eta comma eta becomes, what is the value? Y equal to eta, this will be eta square over 2. Okay. Now that is what you will be having it here. Of course ei is brought in here, so you will have your a3 will be ei okay. No, it has a3, is it correct? 1 minute, I will get it. a3, yeah. Huh? No, 1 minute. What is that? Huh? a3 is, yeah, a3 becomes, huh? I have taken 1 over ei. Yeah, that is why what you, otherwise if you want to write it this entire thing is A3, then you will be having it, this is what you will have. Maybe I'll put it, this term will go here, right? This is what we had, right? Huh? So you will have EI. So eta square over 2. So I can write this as A3 as eta square over 2. Now once you substitute, you can again differentiate it and then get, now where do I write? That is a problem because there is very little space here. Okay. I erase this part, again I come here. Okay. This is the also, okay, let it be there. I will have EI C y comma eta. It will become A3 is eta square over 2, so you will have eta square over 2 y plus some A4. Okay. Now again you have to put y equal to eta. When you put y equal to eta, that is this expression you will have, that is EI C eta eta becomes, this is eta cube by 2 plus A4. From this expression, when you put y equal to eta, this will be eta cube by 2, 6. It will be, what is that, 1 by 3, right? 1 by 3 or 1 by 6? 1 by 6. This is, if I take it 6, this is 3. No. 2 by 3. What? Not 2 by 3. 1 minute. This is, 1 by 3. Yeah. So you will have, this will be EI eta cube over 3, this one. Now A4 becomes, no, is there something I missed here? No, there will not be any, oh no, there is no EI. Okay. So A4 becomes eta cube over 3 minus eta square over 2, which will be 6. A4 becomes eta cube over 6. Now you can write your function. Maybe I again go here and erase the whole thing. You will have EI C y comma eta is eta square over 2 y. A4 is minus eta cube by 6. Okay. Now otherwise I can write my C y comma eta is 1 over EI eta square over 2 y minus eta cube over 6. This is for y greater than eta, and you see y less than eta, that is this expression C y comma eta is 1 over EI. I am writing it, repeating it the same thing, that is eta y square over 2 minus y cube over 6 for y less than or equal to 8. Okay. This is for this and this is for this. Okay. Now you see the symmetry here. I can change y to eta. If I change y to eta, this will become y is eta, eta is y. And so the flexibility influence coefficient function is also symmetric. Now using this function, you have to write the total deformation of the structure. Now how do we write that deformation? Because first we will take it, because you know that this is the function. We want I erase this part. Now you can have W at y. This is the how we define 0 to L C y comma eta. This is how we have defined. We need to substitute this function C. So what you do is, we will split this function into two parts, this integral. We will write it as integral 0 to y. That means you are considering the load that acts on the beam till the point y. That means eta less than y. Eta less than y is, sorry, eta less than y is this function. You follow? What you are doing is, you are splitting the integral into two parts. Please understand, I am putting it, this is wy. I am splitting the loading. That means 0 to y. Here I will have what loading is z eta d eta. Eta I am going from 0 to y, but my y is outboard of eta. So y is outboard means this is the one. Okay. So I will be putting 1 over ei eta square over 2y minus eta cube over 6, okay, z eta d eta. Okay. But here y to L, again I will have z eta d eta. I am measuring the deflection at y. The loading is beyond that point. That means eta is beyond y. That means this function. So I will put this function here, which is 1 over ei eta y square over 2 minus y cube over 6. Okay. Is it clear? Because this is a little confusing, always people. No. Is it? See, this is, always the confusion arises here. The confusion is this integral is what? You are measuring the deflection at point y, right? The loading goes from where to where? 0 to y. That means where is the loading? Loading is inboard of the deflection point. Loading is inboard of deflection point is where? This is loading. Y is greater. Y is where you measure. So loading is inboard of deflection point. So that is why the first one. Okay. And in the second case, the loading is y to L. That means loading is outboard of where you measure the deflection. Okay. Eta is outboard of where you measure the deflection. That is why this function should go there. Okay. Is it clear? Because I know that this is always a confusing thing for many students, and even sometimes we get confused. Okay. Please understand, this is the where you apply the load, where you measure the deflection. Whether the load is outboard of deflection point or load is inboard of the deflection point. That is all. Okay. Now you have seen here very interesting relationship. Okay. But getting C is not that easy, because you have to solve like this. Okay. It's a very simple problem which we have solved. Now you can take a plate vibration, you can take a torsion beam, you can do anything you want, torsion of beams. You can solve this. But how it is mathematically represented is, you know, the equation of motion for a, sorry, not motion, equation for beam bending. Very simple, because this you must have, I'll just write it mathematically, because how will you write the beam equation? Okay, now I erase this part, because these are all just mathematical. See, you will have, you take a small element of the beam, and this is acted on by a load. This is dy. What will you say? You let us say this is the shear force at, this is the downward shear force V. This is the V plus dV by dy into delta y. You can call this as delta y, and then you can have a moment. Here you will put a moment m, bending moment, m plus, right. This is the standard beam. A small element of a beam you have taken, okay, and you have put on the right face whatever the shear force and a bending moment. Left face the shear force and the bending moment. Now you write the equilibrium of this element. Force equilibrium, that means all the forces. This is just force equilibrium. Because this is just a, you will write what? Zy into delta y. That must mean this is V and minus V. So you will have V plus dV over dy del y minus V plus z y del y, and this will give you dV over dy is minus z y, right. Then you take a moment equilibrium. This is force equilibrium. Then you can write moment equilibrium. Moment. Okay. You can take moment about the midpoint or moment about this point. You can take. Okay. If you take moment about this point, you will have m plus dm by dy del y and then this into this distance. So you will have v plus dv by dy del y into delta y moment, because all are counterclockwise positive. And then z, you take it as though this the resultant is acting in the middle. You may take plus z y delta y into delta y over 2, and then minus this moment 0, you will write it. Okay, this is the moment equilibrium. Then what will happen? This moment will go up, moment will go up. Then you say in the limit you divide by delta y throughout, and then set delta y goes to 0. Then what will happen? If you divide by delta y, you will get m by d capital M by dy plus v into delta y, right? Plus v equals 0. That's what you will have, right? Now you come here. You had one equation here. This is the force equation. Moment equation says v plus dm over dy is 0. Okay. All right. V equals minus dm by dy. So you say shear force is minus, but you know dv by dy is okay. You differentiate this once. That will become dv by dy becomes d square. So you will have minus d square over dy into m. But you know moment based on elementary theory, moment is ei d square w over dy square. Put it here. What will you have? Sorry, this square. D square over dy square of ei d square w by dy square equals the beam equation, right? This is the beam equation. Simple. Zy is the distributed load, and this is the ei. You know, I is the cross-sectional area moment. Okay. Now, if you look at this, I have a differential equation. Please understand, this is a fourth order differential equation. I need 4 boundary conditions. Okay, I need to solve properly. Here, I have a solution which is W in terms of zeta loading. Okay. Now this is what people call it operators. This is a differential operator. The differential operator, we can write it as d square by dy square ei. This is actually operating on W, right? So you may call it, this is structural operator. Structural operator operating on W, okay, gives me distributed load, right? So I am calling this is the structural operator. But what I have written here, W in terms of Z, that means I am writing inverse, yes, the operator is inverted, that's all. The inverse of an operator is basically this is what the whole thing is. Symbolically it is written in this fashion. Okay. Now there are several issues associated with that, because this is a fourth order differential equation. You need to get the solution to that. Okay. And you have to put approximate. If here you can get a closed form exact solution. That is one of the advantages of this. Okay. Whereas this form gives you in the inverse. So all your aeroelastic problems, sometimes people write it as in operator form. W is the deformation. Loading is one. I have an structural operator acting on W. I have an inertia operator acting on W. Z is external load, which is the aerodynamic load, which is again dependent on W. So structural operator, inertia operator, aerodynamic operator. They'll just mathematically write it, represent that form. Okay. Here is this clear? This is the differential equation form. This is the integral. This, you don't say this is a solution, because we still do not know what is that, because that is the aerodynamic load. Okay, that load may depend on W itself. Please understand, it is not that we are saying there is a load. This course we will start studying now. How do we get that? This is purely the structural part of the problem. Okay, starting from influence coefficient. Next, we will study how energy methods are applied for structural deformation. How do you get the approximate solution to the problem? Because EI uniform, you are getting all this Euler-Bernoulli. Suppose EI, that is the bending stiffness, is not constant, because the aircraft wing is not a constant, it is varying. Now how do you do? This is, please, that is why, please remember, I put EI inside. Okay, if it is a constant, I can take it out, then I can write the solution. I can allow EI to be a function of Y itself. Then the solution is not, because this equation solution is obtained with uniform EI property. Please understand. This is not, if I have a variable EI completely, I can't write this. This is an example problem which we solved with constant EI, because that equation we used. Okay, so you have to clearly know what assumptions we have made at what point in getting this solution. This is very general. But again, it is an Euler-Bernoulli beam theory. Okay, this whole thing, this equal to Z, Y. Okay, so next class we will study how energy method is applied for getting the deformation of the beam.